Welcome everybody to what should be today the final lecture, if all goes well. So what's on the menu today? So we've done a lot during the semester. Today I'll tell you a few words. It will be quite short on the database architecture of a system like PostgreSQL. Show you how it's stored on disk and so on, very briefly, because you're not computer scientists. So it's just to give you an impression of what's going on behind the scene. Then I'll give you an outlook towards the future. So basically big data for engineers that will be in spring. I'll also wrap up a few things on the material. Hopefully I manage that in the first hour. And then in the second hour, we'll play a quiz game. I have plenty of questions for you. It's in the style of Ice Kage 100. I'm not sure if you know the TV show. So we'll play it that way. You'll play against Manuel right here. And we'll see if you win or if Manuel wins. That's pretty much for today. Let's start then. So, the database architecture. So, what happens behind the scenes? In the end, everything is stored on a machine, right? But this principle that was invented in 1970, called data independence, is supposed to hide all of that complexity. In fact, when you were using in the exercises PostgreSQL, you were just sitting in front of your Jupyter notebook, typing SQL queries, and the tables would just display magically on your screen, right? Everything that happened on the disk, the files and so on, was all completely hidden from you. That's the magic. And this is called data independence. But in order to understand how all of that works and how it's implemented, at least in the good old system that works on just one machine from the 70s, you need to understand a bit of hardware. So of course, I have to confess, I'm not a hardware researcher, so I don't really know much about the details of how hardware works. I mean, I've still tried a while ago to build my own machines like we did in the 90s. But basically what you need to understand for the purpose of databases is a high-level abstract view of hardware. When I say hardware, I mean in particular here, storage hardware, how you store the data as bits, as you know, as zeros and ones on the disk. And it turns out that there's multiple levels of storage. We have, probably those you know is the disk, which can be a hard drive, mechanical, or by now a flash drive, right? So secondary storage. And you have the memory, the working memory, also called RAM, that is just what happens when the electricity is on and the computer is switched on, then it works on the working memory. And I said volatile here because if you switch off the computer, it's all gone, the memory, but the disk stays. But you have more layers. You have a layer on top of the memory that is closer to the CPU. So the CPU is the brain of the computer. This is where the computations happen. And it turns out the CPU also has some very local memory that's very close to it. So it's very quick to read, but of course it's smaller. And on the other extreme, on the bottom, you have tapes, DVDs, and so on. So by now in 2022, probably it sounds a bit archaic or like, does that even still exist? But yes, it exists. In fact, if you store files on your ETH storage system, ETH is saving it on tapes. Why is that? It's because tapes are actually cheap. It's the cheapest you can imagine in order to get zeros and ones. So there's facilities with huge warehouses where the tapes are stored and little robots that get the tapes. But of course, you might need a few hours to get back your backup if you lost your data. On the other hand, the cache is super fast to access in nanoseconds. But as you can see, tapes are slower to get to, but they also can store huge amounts of data. On the other hand, the cache can store less and is accessed in nanoseconds. And basically, the working memory and the disk, it's in the middle, right? So as an order of magnitude, think that a disk is typically 1 terabyte. Working memory, you know by now, it's 16 or 32 gigabytes on your laptop. The access, so a disk is a bit slower to access, takes a few milliseconds to access bits on the disk. Inside the memory, it's below a millisecond. It's 10 to 100 nanoseconds. So as you can imagine, up there, it's super expensive, the cost per megabyte, because it's super fast to access, and so you get less. And the more you go to the bottom, the cheapest it gets, but of course, it's slower and slower to access. So it's all a matter of compromises. So for the purpose of a database, usually people look especially into memory and disk, because these are the two main places that they are interested in, right? So the disk is where your relational tables in the end have to be stored, right? But of course, they are not going to be stored as relational tables because the disk doesn't know anything about relational table. All it knows about is files and directories, right, that you're probably also familiar with. So we need a mapping and a way that PostgreSQL or any other system can store the relational table as files and directories on the disk, on the physical storage. But the user doesn't see that. During the semester, you never actually saw that. But you can, if you want, you can actually try to find out on your laptop where that is, and you will find somewhere a directory that looks like this. PG is for Postgres. And that's a lot of content, right? Very cryptic. You actually don't really need to understand what there is in there, but this is basically where it starts. And that's the reason why if you switch off the electricity or turn off PostgreSQL and then switch it back on, the data is still there because it's actually stored on the disk. And when you update, it's just going to update something on the disk. So now, how is it actually stored? Well, you already know on the logical level. So on the top here, you have the logical level. So this is the relational table that we want to store. And this is what I'm going to explain how it's stored on the disk. So you know that a relational table is a set or a list or a bag of records, right? The records, this is also called tuple, row. We have plenty of synonyms for that, right? But one row of the table is called a record. And when you store things on disk, it's at the record level. You store each record, all the records next to each other. And how do you store what's within a record? So let's start in the small, and then I zoom out and zoom out and zoom out. Within a record, you need to store here the name that there is here, the address that there is here, the gender that there is here, and the birthday date, and so on and so on and so on. But there is something very nice to having a relational table that fulfills the constraint. Remember the constraints? The same support, all of the tuples have the same column names and the same types. That makes it super easy to store on disk. Why? Because all we need to store on disk is the actual content of the cell here, 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 and here, according to the encoding of the type, and that's it. We don't even need to store the column names at every record. They're always the same, so we just store them once and for all. And here, all we need to store is the actual values. So you see here, I have the name, the address, the gender character, and the birth date, and so on, right? And all of that, for many fields, actually has a fixed length. A date is always 4 for the year, 2 for the month, 2 for the day. Here is 1 character. Here it's 255. Here it's 30. So this is a fixed length. This is a bit additional info that I'm not getting into for every record, right? And basically, this here is a sequence of zeros and ones that are just containing the data of the records. What's really, really nice is that the size here, in that case, the number of zeros and ones here is always the same for every record. So this is a highly regular structure when you have this setting. If you know the size of one record on disk and you want to skip 1,000 records, that's easy, just multiply by 1,000. Imagine that a record has 100 bits, let's say, and you want to skip 1,000 records, just skip 100,000 bits. And this is immediate on the disk, it's random access, so you can directly get there. So it's a highly regular structure. And that's the benefit of having these constraints that I told you about, that it's the same columns everywhere, it's the same types everywhere, it's all atomic values, so it makes it easy to store. But now you're going to tell me, yes, this is all good, but it sometimes happens that some values might have a variable length. You don't know in advance how long it is, right? In the case of a date, you know, in the case of a Boolean, you know, but what about this text field where you don't constrain the size of the screen, of the string? It can be arbitrarily long. So how do you do that? Well, there is a slight extension that basically says that you first store all of the columns, all of the values that have fixed length, and you put those that can vary at the end of the records. So you basically have here the gender, that's 1 character, birth date is just 4 plus 2 plus 2 plus 2 dashes. And here the name might vary, the address might vary, and you just put additional pointers in there that basically point to the start of the name and to the start of the address. You need that because it's not always at the same location. That's why you need the additional information. So here it's going to be less efficient because then it's a bit elastic, right? So the size of a record might vary. You might not be able to skip so easily a fixed number of records, but basically it still works. A bit slower, but it still works. Now, you might think, okay, yes, But what happens if I put an enormous binary value or an absolutely enormous string in there, like 1 gigabyte of string, so something super enormous? Then you don't want to do it like that, because the records are supposed to be small in the sense that it is stored, not too much data. But what you do, and that's actually something we love to do in big data and big data for engineers, what you do is you actually cut the data into slices. And in fact, it's this notion of slices probably inspired the engineers to find a name, because they called it toast. And toast is the way that you are actually going to store gigantic strings or gigantic binary values. That's one cell in the relational table, but that is absolutely gigantic. And what they do is they cut it in slices like toast, and they store it separately in chunks in a separate table, right? Somewhere else, basically, not at the same location, right? So you see, you can store everything in fixed length. If it varies, but it's not too big, you can just put it at the end of every record. And if it's really, really, really big, you just outsource it to somewhere else, to a separate table that contains slices of the strings and of the binary values. Okay, so this is for records. Records are not really big, right? It's just going to be maybe, I don't know, to give you an order of magnitude, maybe 1 kilobyte, 1,000 bytes is a good size for one record. But then in a relational table, you don't have just one record. You might have 100, 1,000, 1,000,000 records, maybe even 1 billion records, right? So how do you then store 1 billion times this, 1 billion times this? So you might think, okay, every time I add a record, let's just put it on disk, right? Or every time I want to touch a record, I just read that record from disk. Every time I modify it, I put it back on disk. That's actually problematic if you do that very often. And the reason is that every time you access the disk, the hard drive, especially the mechanical ones, you need to wait until you start getting the data. Why? Because in a mechanical drive, there's a rotation. It only rotates at a certain speed. And the head that actually reads the bits is at a specific location. So you need to wait until the disk rotates all the way to be below the reading head, and then you can read. That takes, of course, it's just a few milliseconds, but that's actually huge for a computer. So that means that if you keep doing it records after record after record, and every time you wait for a few milliseconds, you can compute, if you do it 1,000,000 times, milliseconds, seconds, you're already at 1,000 seconds. It already is 15 minutes for 1,000,000 records. So you can't do it that way. What is actually done on a drive is that you read in blocks that are called pages, and you don't do it record by record, but you do it block by block. And the idea is that in a block, you store several records at the same time, you access them at the same time, and you write them at the same time. And the way that this is done in memory is that you prepare a page, you have some header on the left, you have the first records that you put completely on the right of the page. And then what happens is that you write your record from the right to the left, like this, when you start adding records, right? So you go from the right to the left, there's always empty space in the middle, and at some point the page is full, and typically a good size is 8 kilobytes, right? So if you have kilobytes records, then you would have 8 records, but of course it could be less if the table is smaller, like if you have 100 bytes per record, then you are at 80 records on every page. So you see, you group them together, and then at some point it's full, and when it's full, you put it back to the disk, but you are only going to wait once for the reading heads to be on top of the data, because you write all of that at the same time together. So you only experience that once for multiple records, right? It's like car sharing with mobility, right? You just do several records at the same time. That's called batch processing. Okay, so what happens is that on disk, you write pages that contain multiple records, and you write pages after page after page after page, but when you read and you write, it's always page by page. Always all the records within the same page, read together, written together. And so when you start writing multiple pages, that's part of the same file, right? A page, a page, a page, and the files on disk are actually stored in that way. So you have plenty of pages. You can actually go all the way to 125,000 pages that is still in the same file that actually is roughly 1 gigabyte. That's called one chunk, and that's one file on the drive. So if you actually look in the PostgreSQL directory, so this is what I showed you here, you have a lot of data, you will find plenty of files that are exactly 1 gigabyte long. And that's because that corresponds to a chunk as described here, that corresponds to 125,000 pages. That's one file. But we don't go beyond that because then it starts to be too big, right? So this is why you limit the size. So you store 125,000 pages. Imagine that there's 10 records on every page, then you have 1,250,000 records in that chunk, in that file. Okay. Now, if you have more than 1 gigabyte of data, you just keep creating new chunks, new files as you go. So chunk 1, chunk 2, chunk 3, and you just keep adding and adding and adding. And all of these chunks that correspond to the same table are going to be in a directory. So this is what you actually have on your disk. You have a directory for every table, and you have chunks that contain each 125,000 pages, and each page contains multiple records. And on these pages, the records are stored like this, every record, right? So it's just 1,000,000 times this. Okay, who has an intuition now about how it's done? Right? You don't need to worry about the details, right? This is just high level to give you a feeling of what it is. You're non-computer scientist, so I really do not expect that you understand it as many details as in the computer science bachelor, of course. Okay, now for some reason, oh, this continues to work. Okay, so on disk, it's actually stored like this. Maybe it was because it was the last slide, because I really didn't want to scare you with more, with the physical level. Yes, so that's what I wanted to show you now. I basically unveiled the mystery on what PostgreSQL actually does when you use it on your Jupyter notebook. This is what happens on the disk, right? And the beauty of data independence is, even though I told you, you don't really need to care about that because this is all done for you by PostgreSQL. And that's the whole motivation of using a relational database management system, because if you actually did it in Python directly or in a programming language without PostgreSQL, all of that you would need to do by hand. That's very, very cumbersome to do yourself. So you're just outsourcing it to somebody else. Okay, any questions regarding this? Then I'll switch to the Outlook. Or did I scare you with so much physical details? Okay. Who has an intuition now? Feels like they know roughly what's going on. Yeah, okay, very good. On Zoom, no questions?
No, I don't think so. There were 2 people asking for the lecture slides. Do we have them uploaded?
Oh, yes, we put them for the last lecture. In the first lecture, I usually keep the surprise to just, you sit back, you relax, you enjoy. That's more the spirit of the last day. But we'll put them, of course, on the online as well.
Okay.
Yeah.
So we'll be offline. Correct.
Yes.
Okay, perfect.
We'll put them. Okay. So then that's it. I'll stop the recording and we'll start on the other sides.